this first video of the Discrete Mathematics playlist, we are going to look at propositions, what they are, and then look at negations, conjunctions, and disjunctions. And we'll also take a look at the truth tables that go along with those connectives. The connectives are the negations, conjunctions, and disjunctions. So our first new terminology here is a proposition, and a proposition is just a declarative statement that is either true or false. So notice I have 5 statements written down, 3 are in pink, 2 are in green. The statements written in pink are all considered propositions because they are declarative statements that are either true or false. The sky is blue is a declarative statement. Generally, what we will do is we will take this statement and we will say, let's let P represent that statement. Or the moon is made of cheese, also a declarative statement. Again, that could be either true or false. I'm going to say false on that one. And I'm going to say that is proposition Q. The moon is made of cheese. Again, it is considered a proposition because it is a declarative statement that is either true or false. Same thing with Luke. I am your father. This is a declarative statement. I am your father, either true or false. I'm going to say that one's false, and we'll say that's R. Now take a look at the difference of the statements that I've written in green. D says sit down. Sit down is a statement, but it is neither true nor false. I can't say true, you have sat down. That statement would have to be you sat down. That's either true or false. But sit down is just telling you what to do, and that is not a proposition. A lot of people struggle with E because they say, well, that could be true or false. And while your thinking is correct, the way that it is written right now is not a proposition. If I replaced X with some value, or if I said where X equals 5, well, now it's a proposition because I can say 5 plus 1 equals 2 is false. Or if I said where X equals 1, then 1 plus 1 equals 2 is true. But if I don't assign a value for X and I just leave it as X, then this is not a proposition because it is not true or false. So propositions themselves are fairly straightforward. Again, we're using a lowercase letter, P, Q, R, S, etc. to represent a proposition. And then what we're going to do is we're going to end up making a compound proposition using these connectives. So I want you to think of these connectives like operators, as I would take 1 plus 2. That's an operator. So these are just operators for propositions. And I've put them all on one page together just to have one page that you could refer back to. They're all called connectives. So we're going to go through each of these in detail in the following slides, but I did want to put them all here. So let's talk about them very quickly. We have the negation, and again, this is how we would use that negation. So I would say not P, and again, I would say it as not, but that is the symbol that I would use. Conjunction is and again, we'll talk about each of these in detail. So obviously I would be taking P and Q. A disjunction is an or, so that would be P or Q. An implication is an if-then, so this is an if P, then Q. And then a biconditional, notice it has an arrow on each end here, says if and only if, so P if and only if Q, and that means they both have to share the same truth value. So again, we're using P, Q, R, S, etc., using those lowercase letters to represent each proposition. So let's get into each of these connectives in further detail. The first connective is a negation, and again, the negation is not, and this is the symbol that we would use. So the negation of the proposition P is not P. So example, if I say P denotes the grass is green, then not P denotes it's not the case that the grass is green. Now, it's silly to write it that way, so we don't. Instead, we say the grass is not green. So let's take a look at these few examples I have here, and then I want to look at some truth tables with you to make sure that this all makes sense. So the first one says, my dog is the cutest dog, which is a true proposition, by the way. So my dog is the cutest dog is my proposition P. If I want to write not P, then it would be my dog is not the cutest dog. So that is not P. Again, we could say it is not the case that my dog is the cutest dog, but it's easier to write it the way we would normally say it in the English language. The door is not open is P. Now again, if the door is not open is P, then if I'm negating something that already seems like it's negated, remember in mathematics is the only place that two wrongs do make a right. So the door is not open, which means the door is open. Again, we could say it is not the case that the door is not open, but in real life we would just say the door is open. Last one, are we there yet? Be careful with this because this is not a proposition. It's not a declarative statement that is either true or false, and because of that, I can't negate it. So let's talk now about truth tables and how a truth table works. So if we have a truth table, essentially what we have is a row for each possibility of the truth values of our propositions. So I want you to think of this as having two parts. So this is a very, very basic truth table that we're going to do. But the left side of our truth table has all of the combinations of the truth values for our propositions. So in this case, if I just have one proposition P, that P can either be true or it can be false. So let's say P, again, represented my dog is the cutest dog. Then not P represents my dog is not the cutest dog. So how does a truth table work? Well, again, on the left side, we're going to give all of the combinations, which is very easy for one proposition. And on the right side, we're going to use whatever our connectives are. And so we might have several columns on each side. In this case, we just have one column on each side, but we might have several depending on how complicated our truth values or our truth table is going to get. In this case, let's look at our proposition P, and here's how a truth table works. Let's say P is true. So here I am, P is true. My dog is the cutest dog is a true statement, which means not P, my dog is not the cutest dog, would have to be false because my dog can't be the cutest dog and not the cutest dog at the same time. Let's say instead that my proposition was false. I said my dog is the cutest dog and that is an incorrect statement. Then not P, which says my dog is not the cutest dog, would have to be a true statement. So that's how a truth table works, is on the left side we have all of the different combinations, on the right side we have whatever connectives we're going to use. Truth tables are going to be very important to us, so that's why I wanted to introduce them to you in this video so that you had a good foundation when we get to our next video where we're going to use them in more detail. Before I continue on to our next proposition, I just want to remind you that in this case I only gave you one proposition. We're going to have several. In fact, our very next example is a proposition where I have to, a connective that requires us to use two propositions. So if I have two propositions, I'm going to have 2 to the n rows, which is 2 squared rows or 4 rows. And really this is all about just how many combinations are there. Let's say I'm using P and Q, and it doesn't matter what the connective is in between there. So we're going to do P and Q. We're going to do P or Q, and we're going to do these in just a little bit, but just so we understand, the left side would have to have all of the values for P and all of the values for Q, all of the combinations of those two. So here's the best way to go about this. If I've got P and Q here, then P could be true and Q could be true. P could be true and Q could be false. Then it's also a possibility that P is false and Q is true, or P is false and Q is false. So notice on the left side, which has two columns, these are my combinations. Now, do your professor a favor and write them in this way. I have a lot of students who do true, true, and then false, true, and then false, false, true, false, and it gets very hard for me to check your work when you're all willy-nilly like that. So do me a favor, keep these grouped together, and then these will alternate, and we'll continue to work on that together. Our next connective is called a conjunction, and a conjunction of propositions P and Q is denoted P with the little arrowhead, basically, Q, and it's read P and Q. So a conjunction is an and one way to help you remember this is this kind of looks like a capital A if you added that little marking in the middle. Now the reason I bring this up is because our next one is going to be the arrow pointing down instead of pointing up. So it's good to be able to keep them straight. For a conjunction to be true, both propositions must be true. So we're going to create the truth table together, but it's also important to think about the fact that P and Q represent statements. So let's say P is, it is raining. Q is, I am home. So if I'm creating my truth table, remember there are two sides to this, and on the left side is where we just give all of the different possible truth table combinations. And since there are two propositions, that means it's going to be 2 squared, or 4 different rows. So I'm going to, this is not going to be a row. This is just going to be where I put my values P and Q. So I need 4 rows. So 1, 2, 3, 4 rows. And of course a column for each of my propositions. So I've got P, Q, and I'm going to list all of the combinations. So P could be true with Q true, or true false, or false true, or false false. So that's all of the combinations. On the right side is always going to be whatever it is that you are doing a connective of. So in this case, we're only doing P and Q, or the conjunction of P and Q, and that's the only thing I will need on the right side of my truth table. Now before we start filling it in, let's think about what this means. P says it's raining, Q says I'm home. For this conjunction to be true, both propositions must be true. So it must be raining and I must be home. So this says P is true, Q is true. It is raining and I am home. The only way for P and Q to be true is for both P and Q to be true. And that is the case here. True, true, so P and Q is true. For the rest of the rows, this row represents, it is raining, I am not home. So that's false because they're not both true because I'm not home. This row represents, it is not raining, I am home, and I am home. So it's not raining and I am home, of course, would still be false because it's not raining. And this row represents, it's not raining, I am not home. Again, false because they both have to be true for it to be true. So it doesn't matter if you put these propositions, meaning to the propositions, but keep in mind that that's what you'll be doing quite often, is you'll be using those propositions, using those statements to write them as letters and then go from there to make the truth table. Another connective is the disjunction. The disjunction of propositions P and Q is denoted P with the opposite facing arrow, so basically a V, and read P or Q. And for a disjunction to be true, either proposition must be true. So when we were talking about a conjunction, both had to be true for the conjunction to be true. For a disjunction, either proposition must be true. So again, when I create my truth table, I'm always going to start on that left side where I'm giving all of the different combinations. And on the left side, again, I've got true, 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 false, false, true, false, false. So that's just the combination side. I haven't done anything yet. On the right side is where I'm going to write whatever my results are. In this case, the connective is the disjunction. So I'm going to write P or Q. And again, I think of a disjunction or the or as being a cup. So if you can put anything in the cup, if either one is true, then the result is true. So if P is true and Q is true, then P or Q is true because either one of them is true. If P is true but Q is false, P or Q is still true because P was true. Only one of them needs to be true. They can both be true, but only one of them needs to be true. If P is false but Q is true, P or Q is still true because Q was true. So the only false value I'm going to have is where both P and Q are false, because neither one is true, and for the disjunction to be true, either proposition has to be true. So that's my solution. The ors can get a little bit tricky. Most of the time in mathematics, we're using that inclusive or that we just talked about. That's the P or Q, and that is saying, for instance, the prerequisite for MA 420 is either MA 315 or MA 335. And by that I mean you could have passed MA 315, you could have passed MA 335, or you could have passed both of them and you can still get into MA 420. That's the inclusive or. That's the one we use most often. There's also the connective or in English, which is called XOR. And that is something like you get soup or salad with your entree. Now, if I'm buying an entree, that means I can get soup or I can get salad, but I can't get both. I mean, I can just pay extra, but I can get one or the other, but I cannot get both. So while we just finished talking about the inclusive or, where we said if either is true, then it's true, and that was true, 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 false. The exclusive or is only true if one is true or the other is true, but not both. So the difference here is because this one had two trues, then the exclusive or is going to return a false value because I can't have both soup and salad. I can have soup or I can have salad, and then of course false false is still going to be false. So hopefully you can understand the difference between those. Now notice the different notation I'm going to use now. This is the XOR notation, which is basically just a circle with a plus sign in it. Up next, we're going to continue our study of the connectives by studying implications and biconditionals. And we're of course also going to look at the converse, inverse, and contrapositive of the implications. Hope you can join me.